I do realize that this is going to be a touchy-feely subject for some, but please hear me out before you kill me. Let's roll. So welcome everyone for Pokémath episode 5. My name is Stefan Eriksson, and today we're going to be talking about shuffling. And no, not that kind of shuffling, but okay, just to get my point across. More specifically, what are we going to be doing today? We're going to be looking at if that 7 is actually the magic number when it comes to shuffling in Pokemon TCG. Even more specifically, how many Riffle shuffles are we going to talk about? I'm sure some of you have heard about this magic 7 somewhere, and we're actually going to look into more, well, does it even apply to Pokemon TCG? And a nice quote here to begin with, it's not really how close to uniform a deck after is a million shuffles, because we could shuffle a million riffles and we'll be uniform. What does uniform mean? We'll get back to that in a moment. But the question more is 7 enough? Well, getting into it, first of all, why do we need to shuffle in the first place? Well, starting by that, we don't want players to know exactly which card they will draw, because that would be considered cheating. It's not everything here is an episode of Yu-Gi-Oh! Sorry, players. But then why not just a quick couple of shuffles? Well, because just a quick couple of overhands or 1 or 2 riffles, say, with a big deck, will still give you some good guess of where a certain card is. That is, it's not sufficiently random at that point. So what the objective here is to try and come up with the recommendation is to what is sufficient to make a deck, well, what is the sufficient amount of shuffles to make a deck sufficiently random? That is that every card in your deck has, well, at least approximately the same probability of being wherever in your deck of cards. So, see if I have everything, we're good. Let's get on. But what is random? No. I realize that's a bad joke, but I let it stay in there. My bad. But okay, what is it? It means that, like I said, every given card in your deck has an equal likeliness or probability of being at any given position in your deck. Okay? This is what we know as being uniformly distributed. So again, same probability of a card having a certain position in your deck. Okay? With that aside, then let's think about it first. If you have a deck of 60 cards, so a standard Pokemon deck, right? How many different arrangements can your deck actually have? Think about it for a second. First card could be 60, next card 50, 58, all the way down to 1. So basically it's 60 factorial for those who know what that is. But what it actually sums up to is more particles that there is in the universe. Well, a higher number than the number of particles in the universe. But yeah, so you get an idea of how big that number actually is. So we can have your deck in, I wouldn't say infinite number of arrangements, but a pretty large number. Okay, so the question then becomes, how do we shuffle and for how long? I already indicated that we're going to be looking at riffles, but just to get it out there, there's many different ways to shuffle your cards, some of which we're going to look at right here. I here demonstrate different types of shuffling. I'm just showing a few. I know there's many more, but starting with the overhand shuffle, as you see here, it's the simplest form of shuffling. And yes, it would often suffice for most players, but you should also know that it would take to properly randomize about 10,000 shuffles, which is inefficient. And this also followed by the second one I show here, which is the Hindu shuffle. It's very much related to the overhand shuffle, although slightly different, of course. Not going to go into detail, just showing here. Then I followed by the pile shuffle, and this is important. Just piling like this does not properly randomize your deck, and at best I find it to be a waste of time, but it does count your deck. However, for the start of the game I give you people that. But I also want to say that I don't believe it's a properly randomized even if you shuffle afterwards. But it is good in combination with other things at least, but not standalone. And finally a quick Swedish shuffle, as you can see. Then now comes the riffle here in the center screen, which will show that's the one we will be working with here throughout the rest of the video, and the one I'm basing this number 7 calculation on, or whatever number we come up with. So what you can see here is that I present a different number of shuffles, but what we're going to be looking at here is specifically the riffle shuffle. Why the Riffle shuffle? Because that's the one that's been mathematically proven to be the best way of shuffling. And Bayer Diaconis, back in 1992, that's ages ago, I was 3 years old back then, they actually didn't really show that 7 was the magic number, but people inferred from their paper that 7 would be the magic number when it comes to Riffle shuffles. So just to get it straight, these are the authors that actually mathematically proven how many Riffle shuffles there should be made in order for a deck to be sufficiently random. Then you might think, but why are people just inferring it's 7? We'll get back to that. But in order to understand where this 7 is coming from, what I'm actually trying to explain you here, we need 2 components first. We need what is known as the Gilbert-Shannon-Reed model, which I'm just going to call a GSR model. And then we need a concept called the total variation distance. These 2 things might look incredibly difficult at first, but I'll try to explain them as intuitively as I possibly can for making you understand where the 7 comes from. Okay, so first of all, let's dive into this GSR model. What it actually does, it's a probability model on riffle shuffle permutations, which essentially just means that when you riffle shuffle, how many different arrangements can it actually have, right? So what they figured out back in the 50s, yes, that's how old this model actually is, they showed that this provides a good match for how humans would actually shuffle. And let me try to explain this a little further. The best way to explain a GSR shuffle is simply just a random cut of your deck, so anywhere in your deck like this. So you cut your deck, and then you would riffle your deck afterwards in this manner here. Just like that. The way they then describe it is when you have cut your deck, which is given by a binomial cut, so it will be a random cut here, given by the binomial distribution, should be on screen. Then after you make a random cut, a card would drop from each of the pile with probability, say this is pile A, this is pile B, then the probability that a card would drop from pile A first into the newly shuffled pile will be A divided by A plus B. Similarly, the probability that it would drop from my pile B here would then be B divided by A plus B. So then you can see by doing the math that the bigger stack would have the bigger probability of having a card drop down to the newly shuffled pile. And nothing stops there from being multiple piles coming from the first pile or second before another pile is joined from the other one. That is simply just given by that probability A divided by A plus B or B divided by A plus B. And that is the simplest way I can explain how the GSR shuffle works. And see here what we can do with this model here, right? So you see now that by doing this model here, you get a pretty good approximation for how you and I would shuffle a deck of cards when we speak about, how to mathematically represent it. That finishes off the one ingredient for what we need for understanding where the 7 comes from. The second thing here is what is known as the total variation distance. And indeed, the total variation distance, well, what is it? We would like to measure how random a deck is based on how close it actually resembles a uniform distribution. Remember what a uniform distribution is? Same probability of a card being at every position in your deck, so there's no difference where the card is, the same probability, right? They can measure this on the unit line here, so the 0-1 interval. 1 would then be never generates the same value. English is going well, as you can hear. But what it is here is that, so if the total variation distance is 1, that means the distribution that you're looking at is as different as it can possibly be from the uniform. It does not generate the same values. That means in our application, it's definitely not random. And you would then expect that the closer you get to 0, the more random your deck would be. And if it hits a 0, it should be exactly identical to the uniform distribution, therefore showing that this deck is sufficiently random. And how did they actually show this, or how we're going to talk about this, is that you would repeatedly apply this model that shows how we would riffle shuffle as human beings. So for each time you run this model, this GSR model, you should see that you will become closer and closer to a uniform distribution. So you should imagine this will be for every application you would, if done correctly, would move closer and closer to 0. And the question then becomes is, how far is enough, right? So, okay. So what they did find was the following. Well, they made this beautiful table That might look very complicated, but what it indeed shows, it shows the total variation distance for different deck sizes after how many riffle shuffles has been made. So we see that the horizontal line on top shows how many riffles has been made, and the first column would show how for what deck size. First notice, there's no 60 card deck here because they didn't consider Pokemon decks at that time. We're going to get back to that discussion in a moment. But if we want to zoom in on just 52, which is a standard deck of playing cards, what did they find? Well, they find that if you would riffle shuffle, 1 to 4 times, the total variation distance would not really drop. That means that it's not random in that sense at all after that point. Even the 5th one, it only drops a little bit. Then starting with the 6th, 7th, and 8th, that's where we start seeing a real decline in this total variation distance. And here is something that kicks in, which is known as the cutoff phenomenon. That is, where is there a sharp decline towards randomness. And this is where people inferred that this means that 7 would be enough. So actually, this is where the 7 comes from. This is where they took and said, hey, 7 shuffles, magic number, because this is where the cutoff phenomenon is observed. Therefore, this is the boundary point where we go sufficiently towards randomness. But a quick view of this table tells you that total variation distance is only like a third, which means that's still pretty far from 0 if you really want to be strict about it. But this is also for practical purposes, which I'm going to also come back to in a moment. But as you can see here, this is based on 52 cards, and this is what they get for the total variation distance. Well, now, what did they exactly find? Because they actually derived a formula to tell you exactly how many shuffles needs to get to the boundary of randomness, to get really close to random, or actually random. They came up with this formula. So a half, so 3 halves, times log base 2 multiplied by n, where the n is the size of the card decks you're considering, plus some arbitrary constant, which can be, arbitrary, right? So for purpose of calculation, they just assumed it was 0. And then by doing so, you get indeed a value of 8.55 shuffles, which tells you, okay, for a deck of 52 cards, 8.55 shuffles. I don't know about your math skills, and I don't want to doubt mine, but 8.55 is not 7. So what they actually found was not 7. The actual formula that they come up with is 8.55, which, if you round it, is actually more close to 9 riffle shuffles. Okay, that's fine for now. So what is the exact magic number actually? Well, let's look more into what Pokemon TCG makes it different. So I have 4 points I want to demonstrate here for why 7 might not be the magic number in this case. So please bear with me as I take you through these arguments. The first one here is, we already addressed this, but I feel I need to mention this. 7 was not even what the original paper suggested for 52 cards, as you might just have seen. That's not just what people inferred from this total variation distance following this cutoff phenomenon, right? So just to point it out a little further, it's actually 8.55, which is not 7, right? Okay, that's one point. I just want to get that one out of the way. Second up, so their calculations were not even based on a 60 card deck, right? So that already makes a difference, and you can already expect that the actual number would be higher. I put the calculation on screen here for you guys, and you see it actually comes down to 8.86 shuffles, which then is even closer to 9 riffles, right? And again, as the game goes on, like for instance for 32 cards, which is taken from their table, 6 may seem as enough, right? If you follow the same total variation distance as they used to, infer that, hey, this is the cutoff phenomenon, right? So you can even see that if the deck size is smaller, like 32 here, we would see that, okay, 6 might be enough if we go for the same total variation distance. Okay. So that leaves us with argument number 3. Well, their calculation is also based on 52 distinct cards. What do I mean by distinct cards? That means that, well, there's only one copy of each card in the deck. And when you play Pokemon TCG, then unless you're playing Singleton, so let's just say a tournament deck. I should be careful here. There might be somebody who play a tournament deck of Singleton. please, I want to hear about it. Write in the comments below. I would like to hear that if you actually participate in a tournament playing in a legit singleton deck. But okay, that's besides the point. That also means in a normal deck, you would typically have multiple copies of a given card, up to 4 copies, except basic energies, which could be a lot more, right? And my argument goes that if you have multiple copies, I would argue that you need less shuffles. I've tried to show you an example here. To demonstrate my point here, as you can see, I took 4 red sleeves, and now I'm just trying to shuffle them using Riffle shuffles throughout the deck, just to kind of show the point here. Okay, if I play multiple copies of a single card, it will easier distribute through the deck in terms of needing less Riffles at the end of the day. Although this is no mathematical proof, of course, but it's just trying to show that, okay, suppose now we have multiple duplicates, then you will see what happens. And by this example, you could, well, if I really want to prove it, that will be a complete publishable paper on its own. So maybe I should do that later. But just to put across the example that if you have multiple copies, you might be able to argue, as I tried here, that less riffles might be needed. Cannot say exactly what, because I didn't calculate it, but you would at least get an idea that, well, we could do with less, right? So that's another factor that plays in. And now for the fourth and final argument that we have here is their calculations does not take the experience of the player into account. And this one is important. Why? Because when we talk about experience of a player, let's take a step back. What is the end goal here? That is having a uniform distribution. Or is it? Right? Because think about it. Humans are not super intelligent. Sorry guys, we're not super intelligent. We cannot all be Rain Man, so we're not all super intelligent or whatever, right? So that also means that we would not exactly be able to tell, where a given card is in your deck, right? So you could actually argue that even after just a couple of riffles, say 1, 2, or 3, you would or I would have absolutely no idea where a given card is, right? So that could be one thing, but it also differs on the level of the player. So say you have a beginner, then you could say 1, 2, or 3 riffles may be enough. Why? Because then they have no idea where the card is. They will not be willing to take a bet on in which half of the deck it is. And that's basically what it comes down to, that if you say you're a pro player, then maybe a few more, right? Because you would be potentially able to see, okay, hey, have a better idea of where a given card is, so you need to shuffle more because, well, I'm more experienced. I know I have a better idea about where a card would be after X amount of shuffles. So therefore, that will argue that you will need even more shuffles. However, in the end, it is not really you want to hit exact randomness, I think. It's also more about what is sufficient, right? And that could also be the argument for, you might calculate 8.5, say 8.55 that we saw earlier with their deck size, right? But that would also might be the argument for why we need actually less. And another thing that actually kicks in here, if I play a tournament game, I don't know about you, but I don't know exactly what the level is of my opponent exact. I don't know the exact skill level. Well, if I play against my brother, that's a different story. I know that his skill level is not mine. Ha ha. But okay, joke aside, we are not actually sure, right? So the question just becomes, in the end, what is important? Is it that we get complete randomness, or is it just how close we are to uniform, or is it like, is this enough? Is this sufficient? Well, I've come up with a recommendation here, and this is where it becomes rather subjective opinion of mine. So, okay. But before we get there, there's one more point I would like to point out here, and that is, you might say that 8, 7, 8, 9, 10, whatever number of riffles is the correct number, but all these decisions, all this discussion I made here should take into relation how much time does it take to actually shuffle, because we don't want to spend half our game shuffling, because then, well, it wouldn't take long before somebody accuses you of slow playing, right? So we need to keep that into account. So that's also an argument for what would be a sufficient number, in the sense we also have to take time into account, right? You could also argue here, this is where shortcuts come into account, so you can reduce the amount of shuffles or the number of times you have to shuffle. But still, you will have to shuffle if you're not cheating. Don't cheat. And this is where I come up with a given table, which is my subjective opinion, so please bear over with me. But what I'm trying to argue here is that the amount of sufficient shuffle differ depending on where you are in the game, or differs English. So if we talk about setup, that is where we have 60 cards in the deck, and officially we have 2 minutes to set up. I don't know how fast you're shuffling, but I can definitely pull off, the 8-9 riffles that needs to be. And if we put in the calculation here, as you see in column 3, for a full deck, I get 8.86. And then comes in practice column, and this is where I change the number. I would typically downgrade a bit based on the factors of, say, experience, the argument that we have, we're not playing singletons, so there's different copies in the deck here, there's multiple of the same copy, and also the time constraint here into account. So 7 seems actually good for setup, okay? But then if we talk about as the game progresses, so look at the first/early game, I would argue that's between 33 and 46 cards in the deck. And then, where does these numbers come from? Let's start by 46. When you start your first turn, assuming your opponent didn't have any mulligans, you have 6 cards in your prizes, you draw 7 cards from your opening hand, plus 1 card from your first turn. That subtracts a total of 14 cards from your deck, leaving you with 46. So that means if your first card you're playing in your turn after that is a search card, and you would have to shuffle, then you're shuffling 46 cards. So that gives an upper bound here of 8.29, as we'll see here. And they will give, on the same, following a similar argument, 7.5 as a lower bound. And then where does 33 come from? Well, I came up with it rather randomly, but I thought about, okay, we see so many players dig deep in the deck. The first thing they do is might play Professor's Research, discard their entire hand, draw 7. Then you're 7 cards further down from the 46. They play at the Dene, throw their hand away, draw another 6, which means that they're 13 cards deeper in their deck, and then they might play a search card. So you could argue you could get a couple of cards extra down before a first search card is, but I've just seen so often that there will be a research play at Dene in either order. Don't know what order is best here, but that depends on the situation, right? But that will leave you 33 cards, which I would say is first turn/early game amount, which leaves you with 7.5 riffles. In practice, I would say that would be 5-6 riffles, right? And then you have the mid game, which would then start at 33 following my table, and I will leave it down at 15. Because when you get down to 15, we're starting to get like, you're deep enough in the deck, the game should have progressed enough at this point to when we go into late game. But for mid game, I get, with the same form they use here, you get 5.86 shuffles, which I will leave again at 4 or 5 riffles, depending on how far you're in the mid game. It's a judgment call, right? And then late game would then be anything less down to 2. Like, I would love to see somebody riffle with 1 card. I dare you. Try it. It'll be fun. I'll try to shuffle in tournament game 1 card in my deck. It looks funny, but okay. And that will leave you with the lower bound of 1.5 riffles, which basically, well, give it 2. And depending on how close you're to 15, it'll go all the way up to 4. But if you have a very small deck, 1-2 riffles, okay, done. And as I marked here, please revisit point 3 and 4, because that's my argument for taking the actual in practice number of shuffles down. Okay, so there's another thing here that I need to take into account before we say what we learned here, is that people may not only riffle, of course. I don't even only riffle. I would typically riffle a lot and then follow with a couple of overhands at the end, like kind of a mixed approach. But the argumentation I put forward here is based on riffle shuffle, because that is what's been mathematically proven to be the most efficient way of shuffling a deck of cards. And also, for the application into Pokémon TCG, well, the best one to pull off, in my opinion. So, what did we learn here? How many riffles? Well, it's actually quite hard to say, right? But I came with a recommendation here. Then you can disagree, you can agree. That's fine by me. You can comment in below. I would love to hear your opinion on this. But I would definitely argue that it depends on a lot of factors. That's easy for me to say. But definitely when in the game, right? And I didn't put it here, but I think that's important too. How many different copies of a card? And I could maybe look into that later, but as I say, this is that would be a monstrosity of a task, so I will try to just, stick with the argument I already put in place. And then the experience of the player. But I would love to hear your opinion on shuffle. So, well, that's what we learned today. So I hope I didn't step anybody over their toes here, but I hope otherwise you enjoyed the video. And until next time. Hey guys, thanks for watching this rather long and to some extent complicated video. I hope you made it this far to watch my end card here, but hey, I hope you enjoyed it, and please don't hesitate to subscribe to my channel if you like these kind of videos and want to see more. Still in the process of building this up, so I hope you show me some support, and otherwise, have a great day. Until next time.